Hi everyone, this is still continuation of section 13.3. We are talking about geometric sequences, and in this video we're going to look at the infinite series. Now again, I want to remind you that a series is when we add up a sequence. Sequence is just the list of numbers. When we start to add them up, we turn it into a series. So we're going to look at that infinite geometric series. Geometric series. And so that means we're going to take our geometric sequence, so our terms in the geometric, so reminder, that's when we multiply each additional term by that common ratio. And I'll put that nth term in there. Put a plus sign in front of there and keep going. Okay, this sequence of adding up continuously does converge. When we say converge, it means we get a finite value. And we'll do a couple of examples so you can understand that. And if it does converge, that happens when the r is less than 1. Okay, so if our r value is less than 1, if you can remember the first video in this section, we talked about what happens when r is between 0 and 1. We saw that these terms got smaller and smaller and smaller. So eventually we're adding basically 0. So we're not really adding anything anymore. If r was bigger than 1, these terms kept getting bigger. So every time we'd add something, it would get bigger and bigger and bigger. When we had negatives, it alternated. So if we had negatives that got bigger, it would get negative, and then we'd add a really large positive, then we'd add an even bigger negative. It would continuously, if you looked at those partial sums, it would continuously go back and forth for quite some time. Okay, well, let's just do some examples. So let's say I'm going to look at 1 minus a third plus a ninth minus 1/27th plus, and it continues. And I want to know, does this converge? Okay, so we are looking at an infinite series because we're adding up some stuff. For it to converge, first of all, it needs to be a geometric series or geometric sequence. So when we look at our terms, are they being multiplied by something? And they are. And the common ratio, the number that they are being multiplied by, is that negative 1/3. And in absolute value, that negative 1/3 is 1/3, which is smaller than 1. Not only do we know that it converges, we also know what it converges to. So if this thing converges, it will converge to that first term over 1 minus r. So in this case, it would converge to 1 over 1 minus a negative 1/3, which is 1 over 4/3, which turns out to be 3/4. And if you started to add a bunch of those, you would see that it does actually get close to that. One that makes more sense to a lot of us is taking, this is a common example, taking that sequence of a half plus a fourth plus an eighth plus a 16th. Okay, and this one is again a geometric, and that r is a half. So it will converge because that is in absolute value less than 1, and it will converge to that 1/2, our first term, over 1 minus a half, which is a half over a half, which is 1. This is the classic example if you're standing at some point and you go halfway, and then you go another halfway, and another halfway, and another halfway. Pretty soon you've got that pie filled in. Or if you take a pie, color in a half. Now the part that's not colored, color in a fourth, color in an eighth. Pretty soon the piece that's not colored in is so tiny that we actually say we get there. It's kind of that idea of infinity. All right, let's do another one. 1 plus 5/4 plus 25/16 plus, and I'll put dot, dot, dot. Okay, in this one, we can see that our R is the number 5/4, which in absolute value is bigger than 1. So this is not going to converge. What we say, if it doesn't converge, we say it diverges. So it will not get zone in on one specific value. In fact, eventually what's going to happen to our numbers is we'll be getting bigger and bigger, and so we'll be adding on more and more. So here we're a little over 2. Now we're going to be adding another 1 and something. Pretty soon we're going to be adding 2 and something, then 3 and something, and continuously on and on and on. So it's going to get larger and larger. I think I'll do one more just so you can see. Okay, this is also a geometric series. In this case, my R is -1 because we're multiplying each one by -1, which in absolute value is not strictly less than 1. So this one will also diverge. If you start looking at what those partial sums look like, so we can kind of see that they do not get close to something. Take my 1, so there's my first one. If I add on the -1, I get 0, then I get 1, then I get 0, then I get 1. They keep going back and forth between 0 and 1. It never gets close to one specific value. Okay, where we can use this idea, there's a couple of places we can see it. But one place we'll see it is when we can write a repeating decimal. A repeating decimal as a fraction. Okay. We have been told all our lives that a rational number, which is a number that can be written in fraction form. Number is a number that can be represented as a fraction. Okay, and then we start looking at some fractions, and we realize that if we look at the decimals, that those decimals will either terminate, stop, or they repeat. Okay, so like 2/4 is the same as 1/2 or 0.5. 1/3 is at 0.3 repeating. Okay, what they don't tell us is, unless it's a common decimal that repeats, how do we go backwards to that fraction? And sometimes having it in fraction form is more accurate, because this we have to, if we're going to write it, we're going to stop at some point. So this is actually a more accurate representation of this number. So this is how we actually go and do it. And I'm going to show you two methods. One is using this idea of infinite series. Okay, and we're going to be basically looking at this decimal. So it's going to be 5, 1, 5, 1, 5, 1, 5, 1, 5, 1 forever. And we're going to break it up into that non-repeating part and then also the repeating part. So we're going to look at this piece and then add on the other. So this is kind of like 2.3, and we're going to be adding 0.051 repeating. Okay. And the way I'm going to even break it down even further, I'm going to start with it in decimals so that the connection to the fraction makes sense. So it's this 2.3 plus my 0.051 plus 0.00051. So I'm kind of breaking this 51, 51, 51 up into its pieces. 0.0000051. Each time I'm putting 2 zeros where the one before it would be. 0, 0, 0. Losing my numbers here. 1, 2, 3, 4, 5, 6, 7, 5, 1. And it continues on and on. Okay, now I'm going to turn them into fractions so that we can see that we do have a geometric series hiding in here. All right, I'm going to turn this one in. This is 2 3/10, or I'm going to write it as 23/10. This is the number 51 over, there's 3 decimals, so 3 zeros. This one is 51 over 5 zeros. 4, 5. This would have 7 zeros. 7, and so on down the line. Now if I look at this piece, this is going to be the geometric series that I want to look at. And I did not spell that right, sorry. The O should be here. Okay, where this is my first term, and the R is what I multiplied to get from here to here, which is 1 over 100, which is smaller than 1. So this thing converges or adds up to, again, that formula is your A over 1 minus R. My A is that 51 over 1,000. 1 minus my 1 over 100. 51 over 1,000. And I'm going to multiply it by, this would be 100 minus 99 over 100. So 100 over 99. 51 over 990. So then this decimal can be written as 23 over 10 plus my 51 over 990, which if I got the common denominator and added them together is 388 over 165. And if you do the division, you'll notice that it does give you 2.3515151. All right. Another method of doing this is more algebraic. And that is what I'm going to do next, algebraic. Okay, so what I'm going to do is I'm going to write let x be this number, that 2.3, and I'm going to write out some digits. And I'm going to put dot, dot, dot. So hopefully that makes sense. And I have 2 digits that multiply. So what I'm going to do is multiply it thus by 100. The number of zeros is going to match the number of digits that repeat. And I'm going to put that above here because it's going to be bigger. So that's going to basically move my decimal twice. So I'll have 235.1515151 dot dot dot. Okay, now what I'm going to do is take these 2 equations and I'm going to subtract them. This will give me 99x. Subtracting here, the nice thing is when I multiplied by that 100, it shifted these 5 ones up so that they all matched. And thus I'm going to just have 232.8 8. If I multiply both sides by 10 to get rid of that decimal, and then dividing by the 990, I get this, and we can reduce this. You will notice that there is some nice numbers in both of them, namely the number 6. In fact, there's actually a 2 in both. I would have started with that. And we end up getting the exact same result. This one is sometimes taught in algebra classes because it is a nice way of using 2 equations to find that answer. But we can reaffirm it as well with the infinite series. So this concludes the section on geometric series and sequences, and actually this concludes all of our material for this course. I will see you when I see you.